Welcome everybody in a series of motion. This time we are going to study velocity time relation based on the graphs we have seen. So here we have a graph chart. We have one graph chart. In this, y-axis represents the velocity and x-axis represents the time. Here you can see point A U. It represents the initial velocity from where the acceleration is going up at uniform straight to point B. We drawn a parallel line to the x-axis here we so that can OA is separately denote the initial velocity. So we know that this is the initial velocity parallel to this one. So as we know here, this BC equals to BD plus DC, which is equal to BD plus OA, as DC is parallel to the AO. So substituting BC equals to V final velocity and OA equals to initial velocity, we get V equals to BD plus, you should notice here that BC equals to initial velocity BC and OA is equal to initial velocity, sorry, V is equal to final velocity, and we get V is equal to BD plus U. So here on BD equals to V minus U. This is going to be our first equation, BD minus U. So this BD will be point. From velocity time graph we know that change in acceleration upon time, sorry, this should be velocity, change in velocity equals to acceleration. Okay, then according to this, our BD is the change happened in the graph, so BD equals to V minus U, acceleration upon time. So now we can write it down, BD upon AD, the time BD upon AD, change in velocity upon time. Now we can substitute it, BD upon OC as time. So we get acceleration is equal to BD upon time, or BD is equal to acceleration into time. So as we know, BD is equal to V minus U is equal to AT. So for the velocity we write it as initial velocity plus acceleration into time. This is going to be our first equation of motion. So I would like to repeat the things in short again. We saw this, here we have a graph, here we have a graph, this axis show velocity, this axis show time. Here OA is initial velocity. From this move, the changing velocity happens at uniform acceleration to point B. We draw a parallel line to the x-axis to E so that EA can be the final velocity. So according to this, BC equals to BD plus DC, that initial velocity plus final velocity, because this is also parallel to each other. So BD plus OA, we substitute DC to OA to the initial velocity. Now substituting BC equals to final velocity and OA equals to initial velocity, so we get V equals to BD plus initial velocity. So as now BD is equal to V minus U, this is going to the first equation, and as we know, according to the acceleration formula, change in velocity upon time is equal to acceleration. So our change in velocity is BD, which is equal to V minus U, and time is AD, which is parallel to the OC. So we can substitute OC here. We get acceleration is equal to BD upon time, or BD is equal to acceleration into time. Now we here the U will go this side, so it will be velocity equals to uh, initial velocity plus acceleration into time. So we can find the velocity of any motion through this equation now on. This was our first equation of velocity time relation for position time relation F, that means for distance or displacement. So as we know from the previous graph, our formula was displacement, distance or displacement is equal to area of trapezium OABC, which is equal to the area of rectangle plus area of triangle. According to the formula, we have OC into OA, OC into OA, length plus breadth plus half into base into height, AD into BD. Substituting OA is equal to U and AD is equal to T. So according to that, our S is going to be U is equal to congruent or same as T. U is equal to congruent or same as T plus half T into AT, because BD equals to acceleration. In from the previous we know that BD equals to acceleration, which is we are using here as BD equals to acceleration to time and AD equals to time, and initial velocity is congruent or equal to the time from the starting. So, or we can write it down as distance equals to UT plus initial velocity into time plus half into AT square. This can be our second formula to find distance, which is position time relation. Summarize it once. So area of the trapezium is equal to OABC. Why are we taking the areas to find out the position? As we know, we can do this from the previous graphs. So area of trapezium, area of rectangle plus area of triangle, which is OC. OC equals to OA plus half into AD plus BD of area of triangle, and we are substituting OA as initial velocity, AD as time t, and acceleration into time from the previous equation. So S is going to be U is equal to congruent or equal to T plus half into T into AT, or S is equal to U into T plus half into AT square, that is equal to initial velocity into time plus half into AT square. As we know from the here to find position, we have to find the area. So area of trapezium is equal to sum of parallel side into height. Sum of parallel side OABC into height, that is OC, upon 2. On substituting OA equals to initial velocity, BC equals to final velocity, and OC equals to time t. We get here S equals to U plus V upon into T upon 2. From velocity time relation we get T is equal to V minus U upon A. Using this equation here, adding this equation here, we get S equals to V minus U V plus U upon 2A. How did we do here? From this equation we get V plus U equals to T into T upon A, and from velocity time relation we know time is equal to V minus U upon A. I mean velocity upon acceleration is equal to time. So we add this equation here and we get V minus U into V plus U upon 2A. So this is going to be our next third formula for position velocity relation to find out distance, or we can also write it as 2as is equal to V square minus U square. So here friends, our motion chapter series is going to end. Many students can get confused with the position time with the equations and graphs, but when we are going to add the videos on the numerical methods, the doubts of many students can get solved. So I request them to please wait for some time to get me launched the numerical videos. Thank you.